Hi everyone. Um, Today I'm going to talk about something that based on a dissertation talk that I gave at the University of Maryland um, on June 10th. And the title of my dissertation is Quantum Circuits for Chiral Topological Order. And those people are my committee members. Okay. So, so let me give you the introduction. So as we all know that quantum computers are very important, and quantum simulation of quantum many-body systems is one of the primary applications of quantum computers. And the idea is that we can use quantum computers to simulate strongly correlated systems to find better materials and understand complex physical phenomena. So some physical phenomena interesting to condensed matter physicists are those following topics. So here we'll have quantum Hall states. So what quantum Hall states are, so basically there are some systems that have that have quantized Hall conductance. So Hall conductance is measured by dividing the voltage drop here by the current current along this direction. And it was found that the Hall conductance can be either an integer value or a fractional value. So if it is an integer value, then the quantum Hall states are called integer quantum Hall states. And if this is fractional, then the states are called fractional quantum Hall states. So some other phenomenon that people are interested in is the so-called high-dimensional superconductors. So basically you can see, maybe you can watch it on some YouTube videos that if you have that maybe you can see that you have some on some YouTube videos, you have some like levitating objects in the presence of a magnetic field. Yeah, and then this kind of high-dimensional superconductors can be useful for magnetic trains to transport passengers. Yeah, and another research area that are interesting to condensed matter physicists are the quantum spin liquids. Is the quantum spin liquid. So basically, quantum spin liquid was originally proposed by Philip Anderson to better understand high-temperature superconductors. And so quantum spin liquids are basically strongly correlated spins on a lattice. And sometimes they feature very exotic excitations known as anyons. And then another thing I want to make is that a quantum spin liquid, some of the quantum spin liquid are toy models of some, or maybe some that are related, tightly related to some quantum Hall states here. And another topic that people are interested in is the so-called topological phases of matter. So this is actually a field that is originally like comes from the study of quantum Hall states and quantum spin liquids. And so basically, what people do is that they found that there are some systems, for example, some quantum Hall states and quantum spin liquids that have to be studied through the lens of topological quantum field theory, or sometimes they have to be studied using some tools from algebraic topology. So these are the topics that are interesting to condensed matter physicists, and even though I try to list them separately, but they are interconnected research areas. Okay, so recently teams from Harvard, MIT, and Google have probed quantum spin liquids using quantum computing devices. So this development makes it exciting to explore the preparation of other strongly correlated systems. And my dissertation focuses on one class of such systems known as chiral topological phases of matter. So what are chiral topological phases of matter? So basically, they are systems that have chiral age modes on the boundary, robust chiral age modes on the boundary, and they are topological. And because of those chiral boundary, one unidirectional like age mode, we can understand that this system do not preserve time reversal symmetry. And some examples of chiral topological phases of matter include integer quantum Hall states and fractional quantum Hall states I mentioned. And there are also some other systems. For example, the P plus IP topological superconductor, the Ising TQFT, and chiral spin liquids. So in this dissertation, we aim to explore quantum circuits that can be utilized to prepare chiral topological phases of matter. So we specifically focus on a class of quantum circuits known as the entanglement renormalization circuits, where the multiscale entanglement renormalization ansatz is the earliest realization. So I will talk more about what those things are. And for now, you can just basically understand it as a class of circuits which has a hierarchical arrangement of quantum gates roughly depicted in the following picture. So this is the outline of my dissertation. So in chapter 2, it talks about, the title is Scaled Invariant Continuous Entanglement Renormalization of a Chern insulator. So in this chapter, we talk about how we construct a continuous mirror circuit, or C-mirror, for a continuous Chern insulator model. And this work has been published in here. And in chapter 3, we talk about, the title is Entanglement Renormalization Circuits for Chiral Topological Order. And in this chapter, we talk about how do we construct entanglement renormalization circuits for the wide class of chiral spin liquids. And this is put in this archive preprint repository. And so what's interesting, let me briefly let you know what the connection is between these two chapters. So in chapter 2, this is like a circuit for a non-interacting model. But in chapter 3, it's about how we construct a circuit for an interacting chiral topologically ordered system. So it is kind of a more advanced than this this chapter. And our focus today will be about chapter 3. So the outline of this talk is the following. So first, I will talk about a take-home message before delving into the details of chapter 3. Then I will talk about how I can construct the chiral spin liquids. What are the chiral spin liquids that we're going to discuss? Then I will talk about how we construct the circuits for these chiral spin liquids. Then I will provide a summary and outlook. So here's the take-home message before delving into the technical details of our construction. So in this work, we propose exact entanglement renormalization circuits for a wide class of chiral spin liquids. So just to remind you what chiral spin liquids are, so basically chiral spin liquids are quantum spin liquids we talked about before, but they have chiral age modes, robust chiral age modes on the open boundary, depicted in the following picture. And they can and also it's interesting to know that they feature excitations known as anyons. So anyons are basically objects or quasi-particles that are beyond the dichotomy of bosons and fermions. They are beyond bosons and fermions. So and this word is kind of interesting because in general, finding exact circuits for the ground state of any given many-body Hamiltonian is hard because it's related to the rapidly growing research area of circuit complexity of quantum states or state synthesis and complexity theory. So it is not entirely obvious to construct circuit for any quantum state. So our exact result is kind of interesting, and we're hoping that our exact result can be a cornerstone for future construction of other circuits for other systems. So what are the corresponding liquids we consider here? So basically the corresponding liquids we are considering here are exactly solvable chiral spin liquids that we will construct through bosonizing new layers of px plus IPY topological superconductors. And the resulting spin liquids can be thought of as layers of px plus IPY topological superconductors coupled to a Z2 lattice gauge theory. And it can be shown that our construction falls into Kitaev 16-fold-way classification, which is based on the paper by Kitaev in 2005. So what do I mean by bosonizing, and what do I mean by px plus IPY topological superconductors? I will talk about that in the following slides. So let me talk about what is bosonization. So let's start with the fermionic systems on the square lattice. So instead of putting fermions on the vertices, so here we are putting fermions on the faces or the plaquettes, the centers of the faces. And as we know that any fermionic theory can be written in terms of creation and annihilation operators. So what we're going to do right now is that we're trying to decompose them into so-called Majorana modes. So Majorana modes are basically these operators that satisfy the following anti-commutation relations. And so it turns out that the whole fermionic theory is generated by the following fundamental generators. So we have horizontal hoppings depicted here, and we also have vertical hoppings depicted here, and fermion parity operator depicted here. So the whole theory is generated by the following three types of fundamental generators. And what bosonization does is that, so bosonization is based on this paper, but so for now, let's please ignore what you have learned or other connotations you learn about the word bosonization. So for us, it's just the following two-dimensional mapping. On this map, map the fermionic theory to a spin theory, a spin 1/2 theory, subject to the following constraint, known as the zero flux constraint. So but here we put spins on the lengths of the square lattice. And yeah, so and the constraint, zero flux constraint, is the following 6-body operator. So we have 1, 2, 3, 4, 5, 6-body operator, but it's acting on every vertex. Yeah. So this mapping map the following this operator into this operator, and this operator into this operator, and this operator, the fermion parity operator, into this 4-body operator. So basically what it does is that um is that for the spin on the spin side, we can roughly what this by the way, I forgot to mention that so this mapping preserves the commutation relationship between those operators, the fundamental generators. So we can check that the algebra is preserved, so it's an algebra homomorphism. So basically, you can think of the corresponding like spin theory as a spin theory that have fermions as emergent excitations. Yeah. And so here we have a zero flux constraint. And instead of putting a constraint, we can also impose a constraint by putting a penalty term, like with a large with a coefficient which is very large, to penalize FV has to be equal to 1. So that it can be like we have a Hamiltonian where the subspace of the entire Hilbert space is given by it has to be restricted to have F nu equals 1. So if we violate these constraints, it turns out that what happens is that we will have Z2 gauge fluxes at those vertices, and in the presence of Z2 gauge fluxes, it will induce vortices to the fermions, emergent fermions around those points of violation. So what is a PX plus IPY topological superconductor? So the PX plus IPY topological superconductor is expressed by the following Hamiltonian. So here we have a picture to help you understand what this Hamiltonian is. So basically we can have hoppings and pairings. So here each arrow here has its own meaning. So the arrowhead here represent a creation operator, and the arrow end here represent an annihilation operator. So here we have an annihilation, a creation operator, and here we have annihilation and a creation operator. So we have horizontal hopping, and we have a vertical hopping. And here we have two creation operators. And so this is a horizontal pairing. And here, this is a vertical pairing. So notice that there's a phase difference between these two pairing terms. So here we have I here. So that's why it's called a PX plus IPY topological superconductor. And other than those, the hoppings and pairings, we can also have a on-site chemical potential term. So this is the full expression of the Hamiltonian. So here in this picture, I didn't draw the Hermitian conjugates of those terms, but please include that in your mind. So if we're in the following region, the system will be in the so-called topological region of the PX plus IPY superconductor. So if we apply the bosonization to the PX plus IPY topological superconductor I mentioned on the previous slide, applied on a single layer, will arrive at a chiral spun liquid. And it turns out that this chiral spun liquid will be described by the Ising topological quantum field theory, or the Ising TQFT. I think it's yeah. So what is the so this is basically the Hamiltonian if we apply the bosonization procedure. And I understand that it's kind of complicated, but you can recognize some terms that probably you are familiar with. For example, do you have the hopping terms and the pairing terms, the pairing like pairing strength. And also yeah. and then you have also the chemical potential here. And there are some like operators like W here. So W is basically a product of four Z operators near a phase F. And we also have some like relationships between the edges and the faces around those edges, but it's not too important in our following discussion. Here, I'm just trying to show you that it is possible to analytically write down the Ising chiral spin liquid. Yeah, and you can also include the you remember to include the zero flux constraint, or you can instead of putting a zero flux constraint, you can put a flux penalty term to penalize the fluxes of the spin liquid. So on the previous slide, I bosonized a single layer of px plus IPY. But what happens if we bosonize new layers of like multiple layers of px plus IPY topological superconductor? So it turns out that if we bosonize new layers where new is the layer number, an integer, a positive integer, if we bosonize new layers of px plus IPY topological superconductor with different new, we'll get different chiral topological ordered states. So for example, if we bosonize zero layer, we'll get something called the toric code. So basically it has trivial chirality and it's not chiral. And if we bosonize a single layer, we'll get the Ising T-QFT with Ising anyons, as like we mentioned on our previous slide. And if we bosonize two layers, we will get a state that is in the same phase as Laughlin's fractional quantum Hall state at filling fraction a quarter. If we bosonize three layers, we'll get a state in the same phase as the well-known bosonic Moride fractional quantum Hall state at filling fraction 1. And we can get more and more, and so on and so forth. And the general structure is that if nu is odd, then we will get a non-abelian topological phase. And if nu is even, then the phase will be abelian. So if we want to classify the list of states here by the topological properties of their anyons, it turns out that we'll only get 16 unique orders determined by nu Mach 16. So that's it. And so this is called Kitaev 16 four-way classification, originally classified by Kitaev in 2005. And this Mach 16 like behavior can be roughly understood as like a clock. So instead of like a regular clock with 12 markings on the periphery, now we have 16 markings. So the clock hand goes round and round and round and round. Yeah. So what are the circuits for the chiral spin liquids? For the Kitaev 16 four-way chiral spin liquids? So we will use something called entanglement renormalization circuits, where the multi-scale entanglement renormalization ansatz, or MERA, is the earliest realization of entanglement renormalization circuits. So here I'm just trying to show you a 1D MERA circuit to give you a test of what entanglement renormalization circuits look like. So here at the bottom we have like a state with high entanglement, with maybe could have some complicated entanglement structure. And we want to apply multiple layers of quantum gates, where so for example, after the first layer, what happens is that some qubits are disentangled into the zero states. And for the remaining entangled the rest of the system, So if we ignore those disentangled qubits, they're effectively living on the lattice, like, or one-dimensional lattice with a larger lattice constant. So if we can keep applying this, and then we'll keep getting more and more disentangled qubits, and then we have a relatively small system size here if we ignore the disentangled qubits. So basically for the system here, we have a sparse entanglement. So this coarse graining procedure is reminiscent of the coarse graining procedure you encounter in classical statistical mechanics. So that's why we have a name renormalization in this circuit. And for that reason, the region down here, we will call this as the ultraviolet or the UV region. And the region up there will be called the IR region or the infrared region. And what's interesting about this circuit is that because because all the process involve quantum gates and they are unitary, we can reverse the direction of this circuit. So what happens is that we start with a state here in the IR region with sparse entanglement. Then we can use this type of circuit to generate a complicated a quantum state with high entanglement at the bottom. So basically, it's like we're growing entanglement exponentially. So if the system size is L here, the circuit depth is log L. So like for the fact that it's growing exponentially is a little bit like growing bacteria in the petri dish. So here I'm just give you a test of what 1D Meral in general is might look like. Here I'm trying to here all the quantum gates are like involve only two body interactions, but in I can have a for a more general like Meral circuit, you can also have like three body quantum gates. Some that's also possible, or four body, any finite body ones are allowed. So in general, we'll define general like Meral circuit to involve strictly local gates with respect to the coarse grain lattice at each layer. Okay. And if the system we're interested here down here is translation invariant, then it's also convenient to consider a Meral circuit that is translation invariant. What that means is that, for example, this quantum gate is the same as the quantum gate here, and the quantum gate here is the same as the quantum gate here. And also it is also convenient to have a scale invariant Meral. What that means is that, for example, this gate is the same as this gate, which is also the same as this gate. And this gate is the same as this gate, which is the same as this gate. So besides its like theoretical like beauty, it is also like very useful in practice, because if an experimentalist want to implement this circuit, they can just iterate the same type of quantum procedure again and again and again, and they don't have to use other quantum gates. Yeah. And if a quantum state here can be prepared by a scaled invariant Meral circuit, we'll call this a fixed point wave function. So here I'm trying to show what I show is a 1D what a 1D Meral might look like, but you can also generalize it to like higher dimensions. For example, this is here I'm trying to show you the what the 2D Meral look like for if you want to perform a single step of a 2D Meral. So like originally we have some degrees of freedom, like living on the square lattice, for example. You can also consider other lattices, triangle lattices, or honeycomb lattices. For now, for our purposes, here we just first consider a square lattice. So we can have spins or like fermions living on the edges, faces, or the placates of the square lattice. And we want to find some procedure such that like in the finite amount of time that the system gets coarse-grained in the following sense. So we have originally we have like a lot of degrees of freedom, but then after some procedure, some of the degrees of freedom are being disentangled into like a trivial product state. So if we like just keep the remaining entangled part of the system, they're effectively living on the like a coarse-grained lattice. Like here you can see that the lattice constant is larger than the original. So here just a general idea of what a 2D mirror is. And now let me give you an example. So this is the mirror for the toric code. So for the toric code, like the degrees of freedom are based on qubits or spins. Spin might have spins, and they are living on the lengths of a square lattice. And so what we want to do is that we want to disentangle some spins. So what is the circuit for the toric code? So the circuit is based on the following structure. So we have a bunch of CNOT gates. The CNOT gates are denoted by the following arrows, and the arrow end represent the arrow ends represent a control qubits, and the arrow heads represent the so-called target qubits. So we have a bunch of CNOT gates, and you might wonder like, okay, so we have so many CNOT gates, so some of them are overlapping with each other. What happens if they are like, yeah, so what happens if that overlap? What's the proper order? So it turns out that all those CNOT gates commute with each other, so we don't need to worry about the order of the CNOT gates. So after applying those like CNOT gates, one can show that using the so-called stabilizer formalism that we have some qubits being disentangled. So for example, for those qubits, they're disentangled into the plus states, and for those qubits, they are disentangled in the 0 state. And for the remaining like qubits, they're effectively still living in the torical ground state, but now the torical is defined on the coarse-grained lattice. And the lattice is actually like a horizontally coarse-grained lattice. So it's like all the lattice are elongated like horizontally. Yeah. So this is the circuit for if we apply a single layer of the mirror for the toric code. So we denote it as CZ2X. Yeah, because torical has some interpretation of a Z2 lattice gauge theory or Z2 topological order. This is not so important for our purposes right now. And this circuit is a product of the CNOT gates. So let me just recap what we have done here. So so at the bottom here we have a like in the UV region we have a bunch of CNOT have a bunch of qubits or spins. Then we want to apply a single so-called entanglement renormalization, so that originally we have a system, but then we want to coarse-grain the system. So I forgot to mention that here we're trying to, this is so-called horizontal entanglement renormalization. So we can also do something similar like vertically by rotating the CNOT gates, the whole circuit by 90 degrees. So here for a single layer of entanglement renormalization, it consists of two parts. One is called a horizontal entanglement renormalization. The other is called a vertical renormalization. And this X here represents the horizontal entanglement renormalization, and Y here represent the vertical renormalization. So after we apply these two together, we'll coarse-grain the system and reduce the system to a quarter of the original size. And we can keep applying this to keep coarse-graining the lattices like this. So this is the full mirror of the toric code. And so here the superscript represents the layer, or which layer of the mirror is. So here this is the first layer, and this is the second layer, and this is the third layer, which is like analogous to the 1D mirror, the structure of the 1D mirror you encountered before. So now I've like show you what the mirror for a torical is. So let me now tell you like what are the like circuits for the corresponding liquids. So instead of consider like a general corresponding liquid, let's first focus on the Ising corresponding liquid. So recall that the Ising corresponding liquid here are based on bosonization of the P plus I Py topological superconductor, where the fermions are living on the like centers of the square lattice. So how do we use this structure? Or maybe we can use the original fermion structure to help us construct the circuit. So it turns out the answer is yes. So let me now outline the key idea of our like entanglement renormalization circuit construction for the Ising corresponding liquid. So what we will do is that we will, on the fermionic side, we'll be using ideas from Swingle and McGreevy in 2014. And we will construct a gap path of Hamiltonians that empties half of the sites, while the rest of the sites remain in Px plus Ipy on the coarse-grained lattice. So what that means is that if we can find some like adiabatic path such that at the end, some sites are like a disentangled like this, and the interactions of the Px plus Ipy topological superconductors becomes something like this. So we only have, instead of having like nearest neighbor hoppings and pairings, now we have next to nearest neighbor hoppings and pairings. Then, according to the adiabatic theorem, if we use this gap path, we can go from the ground state of the original like Px plus Ipy to the ground state of the coarse-grained Px plus Ipy. Then we'll convert this infinite time adiabatic evolution into quasi-adiabatic quasi-local unitary that exactly empties half of the sites in finite time. Then we'll convert this, we'll bosonize this quasi-local unitary and apply it on the corresponding liquid state here. So originally we have a fermionic quasi-local unitary, and we bosonize it to apply it to the real like corresponding liquid that we are considering. Now it turns out that after the application of this bosonized circuit, for those like original like empty fermionic sites, the corresponding placates on the spin liquid side correspond to local torical patches. So what it means is that the spins around these regions behave like a toric code. Yeah. What that means is that if you measure the plaquette operator or the vertex operator, they basically takes eigenvalue 1. So because they behave like the toric code, what we can do is that we can just use the idea like we presented on the previous slide. Basically, we can use the C knots I mentioned previously as in the torical mirror. And if it turns out that because the system behaves like the torical around those regions, the result is that half those spins will be disentangled, leaving the rest of the system in the same corresponding spin liquid or the Ising corresponding liquid, but on a coarse-grained lattice. So the spins that are disentangled are represented by the hollow circles here, just like the coarse-grained torical case I mentioned on my previous slide. And here I'm just trying to show you how we do this for Ising-Chiral spin liquid, but a similar idea can be applied to any nu greater than 1, like any chiral spin liquid. Yeah, so let me show you what the whole like entanglement renormalization circuit is. So because recall that here the circuit are based on two types of circuits. One is the quasi-local unitary, and the other is Mera. So we will call our like entanglement renormalization circuit as Mera with quasi-local evolution, and we can abbreviate it as so-called as the English word miracle, which is pronounced similarly to the English like word miracle. So this is the whole like miracle circuit. So first, please ignore the green layers and just look at the purple layer and the yellow layer. So we have a component that is the horizontal entanglement renormalization, similar to the torical case, and we also have a vertical one, just based on like rotating the circuit by 90 degrees. And yeah. So if you look at the horizontal entanglement renormalization, on this object is basically the bosonized version of the fermionic quasi-local unitary that empties half the fermionic sites. And this object, this circuit, is based on strictly local C-naughts, as in the torical mirror that disentangle half of the spins. So yeah. So these two objects are useful for the Ising-Chiral spin liquid. But if you want to consider a more general chiral spin liquid, we'll need to have some auxiliary circuit with involving strictly local gates, yeah, depicted in the as the green layer here, green layers here. Yeah. So here I'm trying to tell you more about what quasi-local evolution is. So what is the quasi-local evolution like on the fermionic side? So originally we have the Px plus Ipy topological superconductor, which is an on-coarse grained system. What we want to do is that we want to find a procedure, find a procedure such that at the end we arrive at the a topological superconductor, a modified topological superconductor in the following sense. So we have those pink sites being disentangled as empty sites, and we only have like next to nearest neighbor horizontal hopping like so we only have hopping on every other sites horizontally, but vertically is still the same. And similarly, we also only have next to nearest neighbor pairings horizontally. So how do we go from the original state I mentioned on my previous slide to the partially disentangled state? The result, actually, the way to do that is to find a gap path. And the gap path turns out to be a direct path that directly interpolate between the initial Hamiltonian and the final Hamiltonian. We're able to show numerically like by like diagonalization, like quadratic by manipulating the quadratic operators to show that it turns out that the whole path is gapped. Okay, so now we have found the gap path. And in principle, we can use adiabatic theorems to go from the initial state to the final state. However, exact adiabatic evolution takes an infinite amount of time. And if we want to do everything exactly, that means that we will wait until the universe ends, which is not practical. So what we'll do is that we want to convert the adiabatic path h of lambda into quasi-adiabatic evolution, which is a unit time evolution under a quasi-local Hamiltonian d of lambda. So the quasi-local unitary is generated by the time-dependent quasi-local Hamiltonian d of lambda in the following expression. And it is interesting to see that instead of having an infinite time, here the time is finite from 0 to 1. And d of lambda is determined by the following expression. Note that the h of lambda is the adiabatic path, the direct path we mentioned on my previous slide. And this is defined by this. The quasi-local Hamiltonian is determined by this. So what do I mean by quasi-local? So quasi-local means that a d of t is written in as a sum of terms d of r of t here. So d of r is basically a term centered at position r. And this d of r can be further decomposed into a sum of terms d sub r, capital R of t. And this is basically a term that is supported on disks centered at position little r with radii capital R. And this d of r has to be bounded by 1 over r to the alpha for any alpha greater than 0, which means that it is decaying faster than any polynomial. In other words, it's super polynomially decaying. Yeah, so this is the construction of the quasi-local unitary. Yeah. So here's summary and outlook. So we have constructed entanglement renormalization circuits for chiral spin liquids that fall into Kitaev 16-four-way classification. So our work also offers a new framework for studying entanglement properties of a chiral topological order, an area where analytical tools are limited. Because we don't have so many analytical tools to study entanglement properties of chiral topological order. So this might be helpful for future research into the entanglement properties of chiral topological order. And we're hoping that this result can be generalized to other chiral spin liquids. For example, there are some chiral spin liquids that are analogs of Laughing states. So here we can only prepare some specific Laughing states, fractional sum quantum hole states. But we are not able to prepare those states right now. So we're hoping that our technique can be generalized to those type of chiral spin liquids. And an interesting question is that can this help us find projected entangled pair states, which is a tensor network for chiral spin liquids? Or can we find other tensor network or maybe machine learning representations of chiral spin liquids based on our circuit result? And another interesting question we can have is that can we generate these chiral spin liquids using mid-circuit measurements and feedback in constant time? Yeah. Yep. So yeah, thank you for listening to my talk. Thank you so much.